Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 2 in the Commodore PET 4016 repair series. If you haven't seen that video yet, I recommend you go check that out first because I'll be picking up right where that left off, and it won't make much sense if you start watching from part 2. I want to mention that there's not much of a series here because in this part 2, I'm actually going to be fixing the machine. So this is part 2 of 2. Anyhow, where we left off in part 1, I had put the clip diagnostic ROM into the machine, kind of hot wired it into there, and we saw that it was pointing to address line 8 as being bad. And when you turn the computer on without that ROM in there, you get this weird floating point value for the amount of free RAM, and the computer just doesn't work properly. There's also an issue where some of the lines of text are cut off as well, which might point to a frame buffer problem. So in this video, I'm going to use this, which is the Romulator. It's basically an FPGA-based ROM RAM replacement for 6502-based machines. It's an open source project. I'll put links in the description below. Of course, you can check this out for yourself. I did a lot of work on this with the VIC-20, showing off how cool this thing is. But with this, we're going to be able to do stuff like replace the ROM or replace the RAM and see if those are the problems, because that's going to isolate where our issue might be. So, without further ado, let's get right to it. All right, I've gone ahead and I've removed the ROM chip that had the diagnostic and all of those jumper leads I had on there, and I have the Romulator installed into the CPU socket with the original CPU plugged into it. The Romulator was programmed for the VIC-20 because that's the last time I used it, so I've gone ahead and I reprogrammed it for the PET. So I loaded the ROMs and the various memory maps and whatnot into the Romulator, and it's all configurable through these dip switches. Check out the video on this for the VIC-20 if you kind of want to see how it works. There are also other ROM RAM replacements for the PET that are available. They are actually more expensive than this one and far less flexible because this can work with any 6502 system. Not to mention, you could load your own custom ROMs and whatever into this, which I don't think you can really do on those prefabricated ones that already have the ROMs programmed into them. All right, so in the top of this configuration file, there are some dip switch settings. Now, originally this was for the 2001-8, but the only relevant switch settings for us are these 4. So the first one, basic 4 with the ROM and the RAM on the PET motherboard. So that means that the Romulator is not actually doing anything. Then we have setting 9 here, so that's the dip switches. That replaces all the RAM. And then we have 10, which replaces the ROMs, and of course 11 is the RAM and the ROM. Now when we say it replaces the RAM itself is running inside the FPGA, so all of the select logic on the motherboard is no longer taken into account at all. And the same goes for the ROM chips. This is the main chip here that does the decoding for the select lines for the ROM chips, but when you actually switch those out with the Romulator, the address signals never even get to the motherboard because they are taken care of inside the FPGA. So that's the benefit of these types of boards, is it actually removes the potential logic problems that you have on the motherboard. What is never actually replaced is the video RAM down here, and that's because the video circuitry on this thing needs to talk to that RAM in order to display any kind of video. So anytime the CPU makes a call to the video RAM locations, the Romulator is set to pass through. So it means it passes through those requests to the motherboard and they're actually written into the video RAM. I went over this stuff with the Romulator video on the VIC-20. But all you need to worry about right now is that I'm going to turn this on set to switch setting 8, which means that the ROM and the RAM on the motherboard are going to be working as normal. So theoretically, we should see absolutely no difference. We should see the top 2 lines missing and that weird banner on basic. So let's see what happens. Okay, there we go. We have exactly the same message, which is exactly what I would expect to happen. It just confirms that the Romulator is working properly, the CPU is passing through, and things are good. So I'm going to power off the machine, and first we're going to swap out the RAM. So that's this first switch and the 4th switch here. Let's see what happens when we turn it on. Okay, look at that! It has 32K of RAM now. Now, of course, the top line is missing because remember I said there was a separate problem happening in the video circuitry or maybe with the CRTC. but we no longer have an issue with that weird floating point amount of memory. Let me grab the Commodore 64 keyboard and plug it in so we can type some gibberish on there and see if I can get it to give me that syntax error. So let's see here. Wait, it's totally working normally now. Okay, so wait a second. So everything is working now. I mean, obviously I'm not able to type things properly, but the @ symbol, which I think I said it would freeze before, is actually the enter key. I thought it was maybe run stop, and we're getting syntax errors as normal. So this computer seemingly is working, but why are the top 2 lines missing? Could this be a problem with my RGB to HDMI configuration? It may well be. So I'm gonna power cycle the computer here. Let's do that again. By the way, you notice how it's just a black screen for a while? That's the RAM check happening, which is completely normal. Okay, so I'm gonna adjust the vertical offset here. Let's just make sure there's nothing. Oh, wait a second, everyone. It's there. What? Was it gone the whole time? Wait, we'll have to disable the Romulator. Oh, that is way too funny. Let's scroll down to the bottom. I know you can't really see. Let's see here. No, we're getting all the text now. Okay, so my config for that is obviously bad. So now when I power cycle this, I can't believe I was doing all that bad diagnostic there. And there weren't even enough lines of text. Oh, that is hilarious. Okay, let's turn this off. I'm going to disable the Romulator again, so it's just going to pass through. Okay, okay. So this is what was happening on the monitor, but the problem is because there's no border on the monitor, I couldn't really tell that there was text that was missing on the top. So when I configured the profile on the RGB to HDMI, I just didn't take into account with the geometry setting that those 2 lines were actually there, that they were just missing. Oh, that is hilarious. Okay, well, look, so that's good. I don't think there's a problem at all with the video circuitry. I think that was completely my configuration on the RGB HDMI, which is good. I'm glad I didn't spend any time troubleshooting that. I should have created the profile for RGB to HDMI on a working Commodore PET and not one that didn't work. That way I know I had all the settings right. Either way, okay, so let's see. With the RAM switched out, this computer works. Now what I did do is I put a copy of PET test on the Romulator. Let's switch that in and let's see if it passes all the diagnostics now. Okay, so for the dip switch is 1011. That should be the PET test. Whoops, I'm moving them all at the wrong time. Okay, there we go. Now let's power cycle this. And I'm expecting the diagnostics. No, it's not working. You know what? That could be my fault. I don't remember what I loaded on here exactly. Oh, wait a second. Oh, I know what's happening here. This is not the same test ROM I was running. This is not the clip ROM. This is one that I think someone wrote in the community. I just had it in a directory. What this does is it kind of goes between the G's, as you see here, and it goes between all these characters. Now, one thing that's interesting is you notice how it's cut off on the top and the bottom. And that's because this PET has 2 different video modes, so to speak. One of them is the one with lowercase letters, and it actually has an extra line between each of the rows of text. And that's because there are descenders on the lowercase letters, and if you didn't have that line there, the bottom of the G would be like right on top of the letter below it. So they added that line, but the problem is even on the real monitor, is it makes the video output kind of taller. So if you have the monitor adjusted where the regular boot up mode takes up the full screen, then when you switch to this mode, the tops and bottom actually go off the top of the monitor. So you kind of have to adjust it in the middle, or maybe you have to adjust it where this one looks good, and then when you display the other mode, you actually have a bit of a black on the top and the bottom. I'll end up creating 2 different profiles for RGB to HDMI, one for the tall video mode and one for the regular video mode, so you'll have to just switch manually. But for now, let me load the other test ROM onto the Romulator. All right, I have the PET tester ROM here in slot 7, so gotta turn those switches on, and I set it up to bypass the RAM because I know that's the problem here. So I'm gonna power this up. All right, there we go. Everything looks okay. It says stack okay, so the stack RAM is working now. Of course, I'm pointing to the regular RAM when reality is the RAM is right here inside the FPGA. Now, fortunately, notice it says remove clip, and that's for the original version that clips onto the CPU, and you're supposed to remove it, which re-enables the ROM chips and continues the diagnostic. There's no way, unfortunately, with this particular device to do that. If I switch the dip switches now to put the machine back into completely stock configuration, it doesn't actually have an effect, at least not on this version of the Romulator. You actually have to power cycle the Romulator for it to reread the inputs from the dip switches. All right, so at this point I have firmly established that it is the RAM that is the problem, or the decoding logic on this machine. How are we gonna figure out what exactly is wrong with this? Well, I'm gonna switch this thing back to just the RAM bypass so we have a working booting system. Let's power cycle the machine. There we go. And at this point, I'm gonna try to use an actual working keyboard on this thing so I can do some further testing to try to figure out which ICs are bad on here. Now this is the actual keyboard I took off this computer. It was the one that I said wasn't working most of the keys. So off camera, what I did is actually took the back PCB off and I cleaned it. There was a ton of dirt in there. I did a little bit of sanding. I did a little bit of cleaning with alcohol, and I haven't tested it yet, but hopefully that's gonna make all the keys work. Obviously I haven't cleaned the top at all, but the inside of the keyboard is nice and clean. So first I just need to test to see if this thing is indeed actually working. Let's power this on again. I don't have all the screws in the back PCB. There's like 4 or 5 that are missing, and I haven't reattached the shift lock wires here. So let's just see how this thing works now. Okay, so we're obviously getting the special characters because I think that shift lock needs to be connected for it to work well, but I can still test to make sure that all the keys are working right. So far, so good, actually. All right, well, all the keys seem to be working except this shift key here seems to be stuck down. I think that's why we're getting special characters on everything. So I guess I'm gonna have to take this thing apart again, which is such a pain because this keyboard, it's very similar to the Commodore 64, but the screws are flatheads, they're not Phillips. So they are super fiddly to try to get in and out of there. So I'm not quite sure what's going on with this shift key. Wait a second, I see the problem. There's no spring on the shift key. So that key must have come off at some point and the spring was lost and someone put the key back on. Thank you very much, whoever you were. But luckily the springs are the same as the Commodore 64, so I'm gonna go grab one. Okay, I stuck a spring key in the shift key and I put all the rest of the screws back in and I put the shift lock wires back on. I didn't really show the restoration of this because there are a lot of videos on restoring Commodore 64 keyboards and it's exactly the same. So if you have a PET keyboard that's not working, go look up online restoring PET keyboard, or even check out some of my previous PET videos where I go over in great detail how to clean and refurbish one of these, including when sanding doesn't work to make the keys work, how to paint on the conductive paint, I guess it is, that will then restore your keys. I had to do that on my 2001, and it's been a while now, and that keyboard still works perfectly, as far as I'm aware at least. Just for completeness, I'm going to switch this back to the way it was with the problem. And I just want to show you what happens on the keyboard when you try to type. All right, so you can see I can type without issue, but when I hit enter, instead of syntax error, it actually just freezes up. If we power cycle the computer, because it's the only way to get back to a working system, even just pushing enter causes it to freeze up. So as I mentioned before, I want to try to diagnose what's wrong with this machine before I start removing chips, and this working keyboard is going to allow me to do that. Well, I think it will. And I'm going to be using the built-in machine language monitor that's on these later PETs with the basic 4 on them. The way you would get into machine language monitor on a normal working PET is you execute a sys command that makes the CPU execute a break instruction. I did a quick Google search here, and there's a couple different sys commands you can run for 1024, or even here specifically for the 40XX series, it's 54386. Those are just memory locations that have a guaranteed break instruction, so when you use the sys command in BASIC, it gets the CPU to execute the break, which will drop you into machine language monitor. So on the PET here in the screwed up BASIC, let's try out some of these. So sys4 was one of them. That just freezes. Another one that was called out for this machine was sys54386, enter, and it just freezes. But now I think what's going on here is BASIC is completely broken, and hitting enter obviously just causes it to freeze. And I think that it applies to every command you type, even any sys command. So this method of getting into machine language monitor isn't going to work. But there's actually another method using hardware to get us into machine language monitor. Here we are on page 3 of the schematics for the PET, and here's the VIA, the 6522, and down here is the 6520. Right here on pin 9 on the 6520, If we follow it up here and over to this connector, pin 20, it says diag. And also if you go up this way, here we are on the user port, and there is that same diag pin again. And sure enough, on these PETs, if you short that pin to ground when you power the computer up, it drops you into machine language monitor. So let's give that a try. It just so happens that pin 20 on the schematic, that one connector is J9 right here. It's the expansion connector. It's that pin right there. So let's ground that and see if we can get into basic. I'm gonna hook up a little clip lead here to it. On the end of the clip lead here, I have a resistor. So I'm just gonna stick this resistor into the RF can here, which is definitely grounded. I know it's on the very edge of the camera there. Okay, let me power on the machine now. All right, it dropped us right into the machine language monitor. Looks like with the M command, you should be able to display memory, and then you can just use the cursor keys to actually edit the memory in the machine. So let's give that a quick try. That just freezes. So I think whatever's wrong with this machine is affecting even the machine language monitor. So let's switch over to having the RAM switched out so we get a working machine. So let's try this again, M0100, 0107. That froze as well. Let's see if this thing is working when I remove the resistor here. Yes. Okay, so we go sys 4. Okay, there we are, machine language monitor without being forced into it. Let's see if the M command works in here. Well, that's weird. It's working here, but it's not working when I force it in with the diag pin. So even though I said that's a good way to get into machine language monitor, I guess you can ignore it because it doesn't seem to work. Whatever that machine language monitor is, does not work. Now, unfortunately, this presents me a little bit of a problem because I was kind of assuming that that machine language monitor that I booted into with the wire would work while the Romulator was disabled because I need that to be able to tell to see where the bad RAM is. What I was going to do is I was going to write to the stack, which is what we're looking at on the screen right there, starts at address 100. And then I was going to go look at the 0 page, like at address 0, and see if it was the same. My hunch is that some or all of the memory is looping. And for normal 6502 execution, especially diagnostics like RAM test, it's going to be writing and reading from memory in the 0 page, which is why it's the first thing it tests. But as it goes to start to test the stack memory, which is starting at address 100, what's probably happening is the reading and writing from the 0 page is actually overwriting parts of the stack memory. When it goes to read back what it wrote to the stack, it's not going to get the values it expects because it's been stomped on by the writing to the 0 page. When the diagnostic ROM doesn't get back the results it expects from the stack part of memory, it flags address line 8 as a problem because reading address 100 or the first byte of the stack is the first time that address line 8 is actually used. But I think the diagnostic calling out address line 8 as bad is just a red herring and is not the real problem, just due to the fact that the ROM is so simplistic about the way it checks memory. Anyhow, I was hoping that shorting this to ground would allow me to do this stuff with the Romulator disabled, and that could hopefully see the RAM problem in effect. I just have one more idea. I'm gonna ground this, turn on the computer, and then I'm gonna pull the wire off. Okay, there we go. So that's off. Maybe that was causing a problem. 0, 0, 0, 0, and we'll just look at that first page. No, it just freezes. If you happen to know why the machine language monitor is not working when I use the wire, put a comment down below. I've never used it this way, so I'm definitely a bit confused as to why it doesn't work, but yet it works if I enter it using the sys command. You know what? I just had an idea. What if I alter the programming on the Romulator to only handle the RAM for the 0 page and the stack? Maybe I can get BASIC working well enough that we can use the machine language monitor, then try to figure out what's going on with the RAM. Okay, yes, I'm going to try that. I'm going to first start by looking at the memory map on the PET. Now this is for the BASIC 2 and BASIC 4 versions, 4080 columns. And you see there starts at 0, and we know that's all the 0 page. And we scroll down through the 0 page here. And then here we get to address 100, microprocessor system stack area. But then look down here, floating point string work area, that's just above that. And we know that that part of memory is messed up. And I wonder if it's like looping around to the 0 page. Remember how it's trying to calculate the basic bytes free? It looks like it's a floating point number, right? What if it's somehow overwriting or getting overwritten by stuff at the bottom of the 0 page? In fact, all of this stuff here seems to be used by BASIC to do stuff. So I'm going to replace from 000 all the way to 3FFF, because it looks like 400 here starts the basic program area. So we're going to leave that alone, and there's the screen memory and stuff like that. All right, so I'm going to switch this to be read-write, which means Romulator RAM for all of the RAM up to 3FF, and let's see if this works. Okay, so the Romulator is done with the programming. Let's pop this off, move that out. Okay, so it's set for setting 9. Let's bring up the monitor. That's going to be the first test here. Oops, I was about to type call -5. -151, which is for the Apple II. That does not work. Okay, so if we look at the memory here, 000, comma, 00FF, obviously that's the RAM that's in the Romulator, so this doesn't really tell us anything. But let's look at the very first thing in the RAM on the motherboard, 0400, comma, 04FF. Now, this part of the memory I don't think is initialized. It should just be all A's. It is. Let's see, let's keep going here through the memory. Let's look at 500. I don't know if you have to have the leading 0. That all looks normal. Let's go up to 1000. 10FF. What are those weird A2s that are all over the place? Let's take a closer look at this. Let's look at 1000 to 1007. Let's just look at that first few bytes. Okay, that's suspect, but that might not be a problem. If you don't initialize RAM, you get like kind of random results sometimes. So let's alter this and let's change this all to zeros. Let's look at what that looks like now. Okay, that's still all zeros. So let's change it all to Fs, which is all going to be 1s. And let's look at what it looks like now. Okay, that part of the RAM seems to be working properly. Let's look at 1100 to 1107. That's similar. It's just got those random 2s in there, but I really don't think it's probably much of a problem. Let's just blanket this all out and see what that looks like. Everything is fine. And let's see how this looks. Oh, did you notice that? That first byte changed from an FF to an F7. The Windows calculator is pretty helpful for this kind of stuff, and I assume OS X has a similar thing. So we wrote FF, and there are all the binary bits that got written to the RAM. So there, of course, there are 8 RAM chips, and notice there are 8 bits. Now we wrote FF, we got back F7, and that is this bit here. When I wrote a 1 to it, I actually got back a 0, and that is bit 0, 1, 2, and 3. So here is a test. Let's write hex 8 to that particular address, that first one. Let's see if we get back a 0 or we get back an 8, because that's also that same bit. It only changes that first bit. Every other bit's 0, and we know zeros work because the first thing I programmed it with was all zeros, and that worked. But then when I programmed with all 1s, which was FF, we got back F7. So I assume when I put 8 in there, that is going to change to a 0. So specifically what we're doing here is I'm going to write 1008. And now when we look at M1000, 1007, that first byte should be a 08. And it is. Oh, I just saw my problem. We're trying to write to 1100, not 1000. Now when we look at this, yeah, there it is, 00. Okay, so that confirms to me that the chip here that's handling bit 3 is definitely bad. Let's see if we can find any other memory locations that have the same issue. So there's AA. Let's change this to 08. So that's working. All right, well, let's exit to BASIC here. Maybe I can write a little program to do a RAM check, like a really rudimentary RAM check across the entire memory space. All right, so I wrote a little program here that said 10 4i equals 1280 to 16383, and I was going to poke 255 to each memory location, and then I would print the what's in it, I'd peek it basically, and then I would poke 0 into it, and then I would print it, and I did next. Then I hit run, and it ran for a while, and everything looked fine. It was 255 and 0. Look what happened. The first line is now messed up. It definitely didn't say that. Like, you can't even type that. So while it was writing to the memory locations higher up, and I started at 1280, which is address 500, and remember BASIC starts at 400, it looks like it's corrupted my BASIC program in the process. So it would imply that there's a little bit of a problem with this memory mirroring that I talked about, where something written up high actually affects the lower down areas of memory. All right, I've written another program here, and I started running it, and it errored out while it was running. So I think that's the memory location that's causing an issue. And we look at the program, it's just 0 to 4096, and I'm starting at address 400. Now, when you look at the screen there, you can see I did a dump of memory from 400 to 440, and that's the BASIC program itself, the one that you see right there. And what I wanted to do is compare how it looked before I ran the program to how it looks now, because clearly something broke in the program because there's a syntax error right there. And notice it says address 3856. That's where I was when it crashed. So on the PET, let's do list. Okay, yep, that completely corrupted the program there. Look at it, what a disaster there. So a bunch of memory locations got corrupted in the BASIC program area. So if we go to the monitor and we look again at 400 to 0F to 440, there it is. And I took a screen capture before and after. So this one here is, I'm just gonna write with my terrible writing after. Okay, so this is after we ran that BASIC program, and this is the before. And you can see some of the bytes got changed. 49 got changed to 41. Let's see what else got messed up here. A 0A here got changed to 02. So 0A, which was 1010, and a bunch of zeros on the left. You just don't see them there. That got changed to 0010. So we can see the bit that got flipped was that same chip. That was the third data bit. It was that same one that we saw messed up when I poked in that higher up area, or I changed that memory location. Remember when I put a 08, it ended up as a 00. That pointed to that same bit as being the problem. Let's look at some of these other bits that got flipped. So we can see 49 became 41. So 49 was 0100, 1001. I bet you it's that bit right there that got messed up. Let's change this to 41, and there it is. 0100, and then that would have been a 1, should be a 1, and it's changed to a 0 again. So we can kind of see that these bit flips that are happening seem to all relate to that one chip. And probably what's happening is the row and the column decoder in that chip, the bad chip, it's probably messed up somehow. So when the computer says to write something to a particular location in RAM, in the stack or in the 0 page, probably what's happening is this same bit flipping stuff is happening. And all the time while the PET's operating, the 0 page is busy doing stuff, and the stack probably is doing stuff as well as interrupts are happening or whatever. So it's probably all stomping on top of each other with those bit flips on that third data bit. So I think at this point I'm pretty confident that probably the only issue with this machine right now is that one RAM chip is bad. So I think it's time to pull the motherboard out. I'll swap that chip out, we'll put it back in, and we'll see if these problems have been fixed. I forgot to mention how to figure that out. It's really easy. You just go to the schematics. We knew that it was data bit 30123. So here it is. We just follow the line. And there it is, UA13. It's also UA12, but that's this one that's not populated on the board. That's for the upper bank of memory, which this machine doesn't have. To install extra RAM, you just need to clean out the holes on all of these blank chips here, install RAM chips there, or sockets and then RAM chips. Anyhow, there's the chip I took out. It's an ITT from 1981, 19th week, 4116. And I have another one to stick in there, a MOSTEC 4116. This one's from 1982, 34th week. So very similar vintage to the bad one. So we just push that into the motherboard like so. Why don't we just set the Romulator for disabled entirely. So that is position 8. Okay, and here we go. Let's turn the machine on. Is it gonna work, or did I make a mistake? Oh, look at that. It appears to be working. It's funny how one bad RAM chip was causing all sorts of weird, crashy problems. So I think what I'm gonna do is I'm gonna reconfigure the Romulator here for the diagnostic ROM, the one I had in the socket earlier in part 1. And let's see, without any ROM or RAM replaced, if at least it passes the normal diagnostics. Actually, you know what? I'm gonna put the regular CPU back in, and let's go back to the EEPROM, which I should still have sitting around here on the bench. Here it is. Here's the EEPROM. So let's put that in. And the reason why is because I kind of want to try pulling it out while the machine is running to see if it'll finish the diagnostics, like remove clip by re-enabling the ROMs and disabling this one. Let's try that. All right, so diagnostics are running properly now. So the question is, can I trick this into finishing running? So what I need to do is I need to take this chip select line to this ROM chip, and I need to give it 5 volts. Oh, look, it stopped running now. As soon as I unplugged it, what happens is that EEPROM starts being selected all the time because the select line goes floating, and it seems like that EEPROM, when it floats, it just chip selects all the time. I need to figure out how to get this to switch to high. You know what? I'm gonna use a resistor to the chip select line that is on the kernel ROM, and then what I can do is I can take another clip lead while this is connected and connect it to 5 volts, which will just bring it high, which should theoretically deselect that ROM chip, and then I can just pull the no ROM off the CPU. And I think that might work, maybe. This might be a fool's errand. Let's try. All right, so here's what I have going on. Chip select line from the kernel ROM is going through this clip lead to this resistor right here. It's a 10K, and that's going to the chip select line on the EEPROM. And then I have this clip lead right here, which is connected to 5 volts. So if I go to this side right here, that's going to the EEPROM, then that should deselect this EEPROM, because EEPROMs are selected with the chip select line down at ground. So if I plug in the 5 volts, I want to see if the computer crashes. It says remove clip right now. It shouldn't, because the way I think is what's happening now is I think it should be running the diagnostic in RAM right now. So it shouldn't mind that the ROM goes away, the kernel ROM. Let's try. Okay. Yep, that worked. Okay, so as soon as I deselected the kernel ROM, the diagnostic scrolled up and now it says no IRQ. Now the thing is, there's a couple loopback connectors here that I have for the PET, one for the keyboard, and I guess this one is maybe for the user port. So one thing that's annoying about the PET is there are 2 edge connector ports here that have the same number of pins. There's the IEEE port for disk drives and stuff, and then there's the user port. Now the IEEE port I think is this one here on the left, labeled J1, this one's J2, and there's a blanking plate on the machine, so I can't actually connect anything to that. And I'm pretty sure that this thing here, it doesn't even have the little dividers inside. I think this is for the user port. So I need to break that blanking plate off and plug this in. All right, so I punched out the blanking plate there, and I have that loopback connector connected there. The keyboard one is connected. Everything I think is ready to go. Let's turn this on. Okay, remove clip. Now, I've never seen this diagnostic run any further than this. I don't really know if there's any footage of it running further than this on the internet. So what I'm gonna do is I'm gonna connect up the 5 volts to this select line here, which disables that ROM, and I'm gonna, at the same time, I'm gonna unplug the no ROM signal. So I'm gonna try to do this all simultaneously. There we go. Okay. Oh, look at that. Video test, okay. Checksum test 87, okay. Oh, wow, 16. Okay, there's a ROM checksum as well. So this is great, because this would tell us if one of these ROM chips is bad, although I'm not sure what the checksum should be. Oh, okay, and it's looping. So it's kind of like the Commodore 64 one in a way. So I'll probably just leave this running for a while just to make sure that this really does work, so to speak. No, this is, sorry, I'm a bit giddy to see this test actually running right now. Like, that is very cool. All right, as you can see, it's been running through and looping, and there's been no issues. I'm gonna say this machine is completely working now. So as I mentioned, the only bad chip is this RAM chip right here, and that's all that was wrong with this computer the entire time. But of course, the Romulator allowed me to do the troubleshooting I needed to do to zero in on exactly what was wrong on this machine, so I didn't go removing a whole bunch of random chips and stuff like that. So I can't stress enough how great the Romulator is, and I think they might be backordered right now, but if you have a Commodore PET or other 6502 based machine, I really recommend you pick up one of these. Now, I'm not sponsored by the creator of this or anything like that. It's an open source project, so it's all available. There'll be links in the description below. You can even make one of these yourself if you so desire. I actually want to mention one more thing. The diagnostic loopback connectors that I'm using here with this diagnostic ROM, these came courtesy of Bill Sealer. Yes, the Bill Sealer from Commodore. He sent me some stuff that he had in his garage, some PET stuff. And in the box was one of those diagnostic clip ROM things. Unfortunately, after doing some reverse analysis on it, it was for an older version of PET. It didn't use the no ROM method that this thing has. It was for the earlier ones. But worse is the wiring that went from the box to the clip-on connector, which I have sitting right here. It's actually this thing right here. This would clip onto the CPU. The wiring that was plugged into this, many of the wires were no longer making good contact anymore. It had these little things here plugged into this, and then the wires came off of this. It looked like it was all handmade, and it just didn't work properly anymore. Most of the wires were no longer making a good connection. But even if that thing had worked, wouldn't have helped in this case with this particular machine because of the whole no ROM situation. But the loopback connectors, of course, came in very handy. So Bill, if you're watching, thanks very much for sending that in. So there we go. That is it for this PET repair. I hope you enjoyed it. I certainly did. Definitely a weird problem, and all down to one bad RAM chip. But I tried to show off the techniques that I would use to actually isolate what the problem is before you go desoldering a bunch of chips on your computer. It's kind of like the recapping phenomenon that goes on the internet. When you have something that doesn't work and people like recap the whole thing, and sometimes that fixes it because the problem was a bad cap, but it's not really figuring out what's wrong. That's just taking like a shotgun approach to repair. And you can do that with a car too. Like your car's doing something weird, well, you can just like change out half the parts and maybe you'll get lucky and change out the one bad part. But ultimately, I feel that for really good troubleshooting, you should try to figure out what's wrong first using logic and reasoning, and then you can zero in on that part and then swap it out. So if you like this video, thumbs up, subscribe, all the regular YouTube stuff. Huge thanks to my patrons whose names are shown up the side of the screen. And I also want to thank the viewer in town who donated this machine. Well, they saved it from e-waste and then they dropped it off at the basement here for me to repair. Obviously, I'm not cleaning the machine up or doing any of that stuff in this video. Cleaning up a PET is something I've already covered on this channel, and there's nothing much to it. You just elbow grease, Windex, you know, all the usual stuff. So anyhow, don't forget to check out my second channel. I'd love to hear about your thoughts about this video and part 1 down in the comment section below. And I guess that's gonna be that. So stay healthy, stay safe, and I will see you next time.